In this lecture, we're going to look at Schrodinger's equation in spherical coordinates. So, just to remind you, here was our time-independent Schrodinger equation. Remember, we had already pulled out the time out of the time-dependent one. That was our time part. That's still always going to stay the same. And then when we plugged in 3 dimensions, instead of the second derivative, it became this Laplacian right here. Now, almost all potentials, real potentials, whether it's gravitational or electrical potential, they're only a function of r. U is usually just a function of r. We call that a central potential. Central potential. Doesn't depend on any of the other angles. Right here. Okay, so all the potentials, the rest of this course will be considered central potentials. U is just a function of r. But we want to look at it in spherical coordinates, so let's just review right here our spherical coordinates. You remember this one's really coming out, but I can't draw it out. And this is your x-axis. This was our y-axis. This was our z-axis, right there. And then we had some point out there, which was in rectangular coordinates, it's x, y, z. But we don't want to use rectangular coordinates. We would rather use spherical coordinates. And so if we have some point there, if we just draw a line straight down to here, we can define the angle that it's off from straight up. We could call that angle theta. Sometimes they call that the zenith angle. And then this length right here, we could call that, say, r. And then if you project this point down to this plane, the xy plane, right there, project it down maybe to right there, then how much it shifted over, we call that angle phi. Sometimes they call that the azimuthal angle. This is the azimuthal, so you come down zenith and then you move across the azimuthal. Okay, it was pretty much the same ones we used for our block diagram when we had our two-state system. Okay, and if we wanted to write out, so now this point is a function of r, theta, and phi. In spherical coordinates, this would be r, theta, and phi. You can specify that point. Now, what's the relationship between the r, theta, and phi's and the x, y, z? Well, if we just wanted to get what the z is, right there, what the z is, the z, just from this triangle, that's r, and this is the adjacent side, so it looks like it's just r cosine theta. So there's your z. Now this vector down here, this line, since this is the x, and this is the other component, this length from here to here would be r sine theta. But I want to know how much of it is along this direction, so we have another triangle over here. So it would be r sine theta times the cosine of phi would be how much along the x. So the x would be r sine theta times the cosine of phi. And the y would be how much along this part of the triangle. You got a triangle right here. And since this is the hypotenuse is r sine theta, and you want the opposite side, then that would be r sine theta sine phi. So y is equal to r sine theta sine phi. So there is how you go from rectangular to spherical coordinates. We already said what the volume element was many times back. We said a little volume element in rectangular coordinates would be dx, dy, dz, but the volume element in spherical coordinates, I think we said before, was r squared sine theta dr d theta d phi. So if you just wanted to find the volume of a sphere, you could just integrate this, and r goes from 0 to big R, and theta goes from 0 to pi, and phi goes from 0 to 2 pi, and you should get the volume of a sphere. Okay, so this is spherical coordinates, and there's a little teeny volume element in that spherical coordinate. So what we need to know is we need to know what is this in spherical coordinates right here. Remember, what this was the second derivative with respect to x squared, plus the second derivative with respect to y squared, plus the second derivative with respect to z squared. And the way you would normally go about and do this, you'd say, well, you'd first think, remember, this is the second derivative of psi with respect to x squared. You could say the derivative of psi with respect to x. Since x is a function of r, theta, and phi, you could say that's the partial of psi with respect to r, dr d theta, plus the partial of psi with respect to dr dx. These two have to be the same because you want that, plus d psi d theta dx, plus partial psi with respect to phi, d phi dx. That's just the chain rule. Okay, I could do that, and I know what the partial of r is with respect to x because I could take the derivative of r with respect to x out of this right here, and so on. And then you could take the next derivative and get the second derivative with respect to x, and then you can get the second derivative with respect to y and the second derivative with respect to z, add them all up, and that would be this term right here. I'm not going to do it. It's a long procedure. If you want to get a lot of practice on partial derivatives, then go ahead and do it, but I'm just going to tell you what that is in spherical coordinates. So that right there in spherical coordinates is 1 over r squared, partial with respect to r, of r squared partial with respect to r, plus 1 all over r squared sine squared theta partial squared with respect to phi squared, plus 1 over r squared sine theta partial with respect to theta of sine theta partial with respect to theta. It looks like a mess right there. It looks a lot more difficult than the second derivative with respect to x plus the second derivative with respect to y plus the second. But it actually makes life a lot easier when you're in spherical coordinates. So this now takes over that little spot right there. Okay, so now if I plug that in, we can write out Schrodinger's equation in spherical coordinates. I think what I'm going to do is, just because I don't want a minus h bar squared over 2m with each one of those terms, I'll multiply everything by minus 2m over h bar squared. So I get a minus 2m over h bar squared there, and I get a minus 2m over h bar squared there, and I don't get any term with that. I just get the psi. So what would this become? This would become, we got this, which is 1 over r squared partial with respect to r of r squared, the partial, now we're taking it with respect to psi, with respect to r, plus 1 all over r squared sine squared theta partial squared of psi with respect to phi squared, plus 1 all over r squared sine theta d theta of sine theta d psi d theta. Okay, so that takes care of all of this. Then we move this stuff over, so it's minus 2m over h bar squared u psi minus 2m all over h bar squared u, which is just a function of r, times psi. And then equals, and we're going to move this over to the other side, minus 2me over h bar squared. H bar squared, 2me over h bar squared, psi. Okay, so that looks like Schrodinger's equation in 3 dimensions, the time-independent and spherical coordinates. Okay, so how do we solve this equation right here? Well, we do it the same way we solved every other partial differential equation we've had. This will be the 3rd time we've done that. We'll do exactly the same thing. We'll say psi is equal to big R, which is just a function of R, times big theta, which is a function of theta, times big phi, which is a function of phi. And plug them in and get rid of the partial derivatives, and that will turn them into total derivatives. Okay, so if we do that, then out of this first equation, since you're only taking the derivative with respect to r, this part can be brought out in front of this term. So we'd end up with a theta sub theta, phi sub phi. Then we've got all this, but now these turn into total derivative because there's only r in front of them. So we got 1 over r squared d dr, r squared d big R sub r dr. So that takes care of this term right here. Then on this one, I can pull out the theta in the r term because this is only taking the derivative with respect to phi. So this is going to be plus. We're pulling out the r and the theta part. And we still get an r squared sine squared theta. And we still got the second derivative. Now it's a total of big phi with respect to phi squared. Okay, that takes care of that term. Then on this one, since we're only taking the derivative with respect to thetas, I can pull out the r's and the phi's. Plus r sub r, phi sub phi. And then we can turn all of our partials into totals. We still got the r squared sine theta, d theta, sine theta, d theta. Okay, that takes care of that right there. Okay. Maybe I'll bring this over to this side, and I can at least factor out the two. I'll bring this over, and this will be a positive, so we'll factor out the 2me over, sorry, not the e, 2m over h bar squared psi. Sorry. I'm gonna bring over factor out the 2m over h bar squared, 2m over h bar squared. They both have a psi in it, but psi was r, theta, and phi, so they both have a r sub r, theta sub theta, phi sub phi. I'll factor all that out, and the only thing that's left with is a e minus u. E minus u of r. And now it equals 0, since I brought that term over. Okay. Doesn't look that much simpler, but it is getting simpler. Now we do exactly what we did on the last ones when we had partial differential equations. After we did this step, what do? We divided by this term. So we will divide every term by r theta phi. R, theta, and phi. We'll just divide every term by that. If we divide every term by that, this just becomes 1 over r. So we have 1 over r sub r, 1 over r squared, dr of r squared dr. It's the first term. We're dividing by r theta phi, so the r's and thetas gone, and I have a divide by phi, so we got plus 1 all over r squared sine squared theta, 1 over big phi, so phi, d squared phi, d phi squared. And then dividing this by r theta phi, these two drop out and we get 1 over big theta, plus 1 all over big theta times of theta times r squared sine theta d theta sine theta, sine theta d theta. Okay, that takes care, plus we're dividing by r theta phi, so this r, the theta, and phi are all gone, so we just got plus 2m all over h bar squared e minus u of r equals 0. A little simpler. Okay. Well, what I think I'll do on the next step right here is I think I'll multiply everything. We'll multiply by r squared sine squared theta. R squared sine squared theta. That's what I'm going to do. Well, what does this term become if I multiply everything by, first of all, the r squares are going to drop out, so all I'm going to get is a sine squared in the numerator here, so I get a sine squared theta all over big R. So that takes care of that term, and I still get the ddr of r squared d big R bar dr. Okay, I'm going to multiply this times the second term. Well, that just drops out right there, and so all I get is the plus 1 all over phi sub phi d squared phi d phi squared. Okay, that's all I get for that term. Then the next term, I'm multiplying by this. The r squares drop out, but since there's a sine squared, it leaves me with a sine in the numerator, plus the sine theta all over big theta. And the r squares dropped out, and the other sine dropped out. d theta sine theta, d theta, sorry, d big theta, d big theta, d theta. So that takes care of that term. And then plus, since we multiplied by this, we're going to get a 2m r squared sine squared theta, 2m r squared sine squared theta all over h bar squared e minus u of r equals 0. Okay, so what do we want to do next here? Well, suppose I took all of this and all of this and put it to the other side of the equation. So if I did that right here, the only thing that would be left on the left side would be this term. So all I'd be left on the left side is 1 over big phi sub phi d squared big phi of phi d phi squared equals, well, what's it going to equal? It's going to equal negative this, and a negative of that, and a negative of that. I don't know if I want to write that all out, but it's going to be negative this, negative, no, I'm not going to write it all out. It's just going to be negative this, that, all of that right there. Okay, doesn't matter. All that matters is that you'll notice that this term, and this term have no phi's in it. They only have r's and thetas. So this right here is only some function of r and theta. And this is some function of phi only. And this has always got to hold for every r, and for changing just theta or just changing phi, this has got to be equal right here all the time. The only way this can ever be true is if this is a constant and that's a constant. Okay, just like we did before. And so we'll just set this equal to a constant, and we'll set that equal to a constant, and at least we're separating it down into smaller pieces. So we'll set this equal to a constant. 1 all over big phi sub phi d squared phi d phi squared equals a constant. Well, what should we call that constant? Well, I think I'm going to call it, just to make life a little easier, I'm going to put it as a minus. Why? Because there's a lot of minuses. So I can make it anything I want. It's a minus. And then I think we'll even, just to make it a little simpler, I'm going to call it m sub l squared. It's not mass. This is not mass. It's just a constant. I can call it something squared right here. Okay, so so that means this other equation, I'm going to set this equal to minus m sub l squared too. So we'll set this equal to minus m sub l squared, and we'll set all of this equal to minus m sub l squared, which means we can cancel at least the minuses over here later, but right now, well, this is what we're going to use. So now I've gotten down to just solving this simple equation, at least for phi. So I took this big one and we're breaking it down, picking off little pieces of it to solve. Okay, so let's just solve this. So what we'll do is we'll multiply by phi to bring it over to this side, and then we'll add it back over to this side. So we end up with a differential equation is d squared phi d phi squared. And then over on this side, it'd be minus m sub l squared phi, but we're bringing it back to adding it to both sides, so it's plus m sub l squared phi equals 0. Well, that looks like an equation that we've already seen many times. That was isn't that just the second derivative plus some constant times that equals 0? Remember, what we said when we used it for the infinite well, didn't we say it was something like a cosine? In this case, it'd be the square root of that, so it'd be mlx plus b sine. M sub lx. That would, but I don't want to use cosines and sines. I don't need to. Remember before, we can write sines and cosines in terms of e to the i's. And so it looks like it'd be a little easier if I just said phi, big phi, was equal to, say, e to the minus m sub L phi with a constant. How about that? Would that work? Oh, so I need an I in there. I, right there. Would that work right there? That is, if I plug that up into here, because did we say e to the I was something like cosines and sines? Do I even need to make it negative right here? No, we can even make it positive. We don't need to make it negative. It wouldn't make any difference, but I am sub L phi. Why? What is the second derivative of this? The second derivative of this, you bring down the I m sub L twice. If you bring down I m sub L twice, that's I m L times I m L, that's minus m sub L squared times C e times the whole thing back again, that's just phi. So if I replace this with this, you can see that it's just going to give me 0. So this works right here. Just this would work too, but this one is simpler. This one's simpler to use right here. So that means that phi sub phi is equal to C e to the I m sub L phi. Now remember what phi is. Phi is going around this way. It's going around. There's your phi angle. And we know that when you go all the way around, it should match back up right here. Why? Because Schrodinger's equation has got to be single valued. So it's got to match back up. So that means if you add 2 pi to this, it should be the same. So that is phi at phi plus 2 pi should equal the same as if you didn't do it right here, because you're right back to where you started from. So let's plug this up into here. We get C e to the I m sub L, and I'll plug in, instead of phi, I'm plugging in phi plus 2 pi. Phi plus 2 pi. That should equal this. C e to the I m sub L phi. Well, the c's drop out. And you notice this is just the product. This is e to the I m sub L phi times e to the I m sub L 2 pi equals e to the I m sub L phi. Well, those two terms drop out. So that means e to the I m sub L 2 pi has got to equal 1. E to the I m sub L 2 pi should equal 1. Well, remember what the definition of e to the I x is. That's just Euler's equation. This is just the cosine of this plus I sine of that. This would be the cosine of 2 pi m sub L plus I sine 2 pi m sub L. Okay, well, the only way that this can be 1 is, this has to be 0 because there's no I over here. So this has to be 0, and this has to be 1. Well, you'll notice anytime m is an integer, this is going to be 0. Anytime n is an integer, this is going to be 1. And it even works for 0, because if you plug in if m sub L is 0, that's 1. And it even works for negative numbers right here. So that tells me what m sub L is. M sub L can be 0, plus minus 1, plus minus 2, ... That's why I said it didn't matter if I put a minus up there, because m sub L can be plus or minus right there. Okay, well, this right here looks like quantum numbers right here. We could call this the azimuthal quantum number. Azimuthal quantum number. Sometimes they call it the magnetic. Maybe that's where the M came from. Magnetic quantum number. Okay, so that's the quantum number that goes around this way, right here. That assumes that everything matches back up. Okay, so now we can plug that back up into here, and we can get our wave function right here. Well, this is our wave function, but m sub l has to be those values right there. So phi sub phi is equal to some c e to the I m sub l phi, where m sub l is equal to 0 plus minus 1 plus minus 2 dot, 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 dot. Now we do need to get that c right there. We can get that from the normalization right there. All we have to do is integrate psi star psi has to be 1. So we know 1 is equal to the integral of phi star phi d phi. Now we know when we integrate over our little volume, where do we say the little volume was? Right here. There are no r's and thetas here, so if you're just integrating over a volume, you just have to use the d phi. If we were integrating over r's, we'd have to put in the r squared dr. If we were integrating over the theta, we'd have to put in the sine theta d theta, but there is no phi's over here, so it's just d phi. And our limits going all the way around, that's 0 to 2 pi. Okay, if we plug in now, this times its complex conjugate. Well, if you multiply this times its complex conjugate, e to the I ml phi times e to the minus I ml phi is e to the 0, which is just 1. So all I get here is just my constant squared, c squared. Because the e's drop out when you multiply by its complex conjugate, d phi from 0 to 2 pi. Well, that's just c squared. Integrating d phi is phi from 0 to 2 pi is 2 pi. And we're set that equal to 1, so that must mean that c is equal to, divide it and take the square root, 1 over the square root of 2 pi. So we can plug that in, and now it's normalized. Phi sub phi is equal to 1 all over the square root of 2 pi e to the I m sub l phi, where m sub l equals 0 plus minus 1 plus minus 2. Dot, 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 dot. So there is the, where we got? We've got this part right here. We'll need to get this and this, put them all together to get that, and then we'll have to put that with this to get the full wave function right here. But we're not there yet right here. We already said that these are normalized right here, but are they also orthogonal to each other? Remember, everything should be orthonormal. That is, if I were to integrate from 0 to 2 pi, two different ones, say, I guess I should put a little m sub l there since the quantum number is m sub l. But if these were different quantum numbers, it should be 0, if they're orthogonal. So how about if we say ml1 star ml2 function of phi d phi. Let me just see if they're, we already said when they're the same you get 1, that's how we normalized it. But let's say they're not the same, let's say they're different. Do we get 0, or they're orthogonal? Well, let's see, well let's just plug in. Let's plug in this down into here. So we're going to get a 1 over the square root of 2 pi with this one, and 1 over the square root of 2 pi with that one. So that's just going to bring out the 1 over 2 pi. And then we get 0 to 2 pi. And then we're going to get e to the I, well, this one's going to be a minus, so we get E, because it's the complex conjugate, minus Im sub, what do we call that, L1 phi. And the other one will be ML2. So it would be e to the Im sub L2 phi, d phi. Okay, I guess I could combine the two right here. So this is 1 over 2 pi times the integral 0 to 2 pi. If we combine them into one e function, it's just e to the, I can factor out the I and the phi, so we get I, and we would get m sub L2 minus m sub L1 phi, d phi. Okay, and now we can integrate that. Gives me 1 all over 2 pi. If we integrate that, it gives me e to the I m sub L2 minus m sub L1 phi all over I, if we integrate I m sub L2 minus m sub L1 evaluated from 0 to 2 pi. Okay, and let me just look at this term right here. What is that term evaluated at the 2? Because these two numbers don't change right here. Well, what does this give me? This gives me, just in the circle, gives me e to the I m sub L, m sub L2 minus m sub L1 2 pi minus, and then we're plugging in the 0. Well, e to the 0 is just 1, so it'd just be minus 1. Well, what does this give me? This was just a number, and this is just a number right here. So when you subtract them, any two of these, right, you still get an integer. It could be negative, it could be positive, but still an integer. So this is just an integer. Okay, so what does this give me right here if you get e to the I, an integer, times 2 pi? Remember, this is cosine of an integer times 2 pi, integer. Let me just write I for the integer times 2 pi. Plus I sine an integer times 2 pi. Well, this is just going to give me plus I sine integer. Integer times 2 pi, sine is 0. That's 0. Cosine of an integer times 2 pi is 1. Because every time you go 2 pi again, it's just 1. So this is always, so this whole thing is 1. If this is 1 minus 1, you always get 0. So these things are orthonormal. That is, this right here is equal to the, remember, m sub L1, m sub L2. They're 0 when they're not equal, and they're 1 when they're equal. And from a linear combination of these, I could make any strange wiggle around the azimuthal direction. So if you were looking down from the top on this, looking at the azimuthal direction as you go around, any sort of strange pattern I have going around, I can write as a bunch of these right here, m's as a bunch of these functions right here. Now, on the next lecture, we'll show what does this m sub L mean right here. What does that help me with right here? Okay.